Welcome you all in lecture 4 of signals and linear systems. So in this lecture we'll cover the rest of the topics of signal modeling. So we'll cover exponentially decaying or raising sinusoid, impulse signal, unit step signal, ramp signal. And we'll also cover some of the examples of all these signals. So here you see that there is so this signal which is actually exponential, which is a sinusoidal signal, but which amplitude is actually decreasing with respect to time. So this is a time domain signal, and if you see the equation here, so general equation is in this nature. So you have a product of two function here. One is exponential signal a to the power minus at, and another is cosine signal with a phase maybe theta naught and frequency omega naught. So as you see here, that your signal amplitude decreases with respect to time, and and uh, and the amplitude of this sinusoidal signal is within and within two envelopes. So one is the upper envelope or positive envelope, which is 1.5 e to the power minus 2t. So you can also say that this is an upper envelope. You can say that this is an upper, maybe upper envelope, and this one is actually, you can say that this is a lower envelope, also lower envelope. So the dotted line shown here is the lower envelope, and that is actually precisely the exponential negative of the exponential signal. So it is written here. So this upper envelope is 1.5 e to the minus 2t, and the lower envelope is minus 1.5 e to the minus 2t. We'll explain it in the next slide in more detail. So this is the exponentially raising sinusoid. So you have a now exponential signal where a is now positive, small a. The exponent of e is a positive integer, or it can be any fraction as well. So now the amplitude of the signal, it raises with respect to time or increases with respect to time, and it goes to basically infinity, as you see here, with respect to time. The amplitude, as the amplitude increases. Now here, as you see, we have tried to plot why we have the shape of the decaying exponential signal. So this is the main signal equation. So it has two parts. F1t is the exponent part, a to the power minus at exponentially decaying signal, so which is shown here, F1t versus t. And then you have F2t, which is a cosine wave with a theta naught. So let's consider the case where theta naught equal to maybe 0. So in this case we have assumed that the theta naught equal to 0. So that's why if you plot here at t equal to 0, you should get a peak for cosine, and then at half of the period you should get a negative peak, and full period you will get again the same peak. So it will be a periodic signal as we have written or drawn here. Now this is the f2t. So the f2t will be always within 1 and minus 1. Will always be within plus 1 and minus 1. So this will oscillate between plus 1 and minus 1. Now if you multiply both of these two, so f1t and f2t, what will happen? So first of all, look at here that you have plus 1, right, in these peaks. So if you multiply these with the exponential function of f1t, then at the location of 1 you should get exactly the same value of the exponent. So exponential function. So you at this time, you should so this is 1. So 1 into the value of f1t at this time, right? So if you multiply this, you should get this exponential values of the total function f2t. So this one is actually f2t. So this one is f2t here. So This one is f2t. We are trying to, we'll plot f2 f2t here, f2t here we are trying to plot here. So again, if you multiply f2t with f1t at this location where f2t has a peak of 1, so 1 into this f1t, whatever value you get, that will come here. Similarly, at this point also you should get the same value of the exponential signal, because it is 1 here, you should get 1. Similarly here, it's almost the value of this one is almost this value is almost 0, so you should get basically a 0 value here at this location here. Similarly, if you consider the negative peaks where you f2t signal becomes -1, then the point in time shown in the red dotted line here. So this value is -1, and you are multiplying this -1 with the exponential signal here. So whatever value you get, that should be exactly the same value of exponential signal with a minus sign. So this is the point here of f2t. And then similarly here, -1, whatever value you get in the exponential signal, it should be multiplied, and with the negative sign you should get this value. Similarly, you get here the value here. So now if you draw it now, you should if you draw it now, then how it will look like. So let me just try to do that. So you have right, and then you should have this thing, probably to oscillate like this, and then you have so this signal is basically your f2t. So this signal which we've drawn, so this is your f2t, which is your a e to the power minus at cos omega naught t, and plus theta naught. So in this case, our theta naught we consider as 0, but it can be any other value. So you'll have a phase shift of the sinusoid. So hopefully you have understood why we get this decaying and raising, and here we have shown for the case of decaying sinusoid. Similarly, you'll get you can easily draw the case for the raising sinusoid, and this kind of signal we'll see in different systems as a system response. And when we go to the time domain analysis, we'll see this kind of responses for a particular kind of system. So next is very important signal, which is an impulse signal, and this plays very important role in our course, linear uh, signals and systems, signals and linear systems. So so as we have said earlier, that delta t, if you this delta t function is a impulse signal. And impulse, why we call it impulse signal? Because it represents a signal that lasts for very short or negligible amount of time or duration with a very high magnitude. So you get very high spike, value of spike with a very short interval of time. And that if that, as we know, that if that is an input to a system, then the response or the output of the system is called impulse response. And impulse response is very vital to characterize a system, and we'll talk more about it later. So let's try to explain more about this delta t. So delta t is equal to is infinity value wise when t is equal to 0, and it is 0 when t is elsewhere. You can say elsewhere, or t is not, so t is not equal to 0. So this represents elsewhere, right? So elsewhere, this is 0. So now if you plot it here, So everywhere it is, so suppose this is t, starts from 0. So everywhere this value is 0, here is also 0, but at t equal to 0 you get infinite value. So this is very high magnitude, so we cannot show these high magnitudes in a paper because your paper has a limited size. So we represent that with an arrow. So this is your delta t. So remember that we use very special notation delta to represents an impulse function. So this is basically the simple definition of an impulse function. Again, you get a very high magnitude of spike at a very short duration, and in this case, for when you have delta t, the duration is at t equal to 0. So you can say that the impulse here, the impulse is the location of the impulse for delta t. The location of the impulse is at 0, right? Okay. Now let's elaborate the concept in more detail. So one problem you can face is that how you can differentiate two impulse functions. For example, one is delta t, another is tan delta t, right? Delta t and tan delta. How can you differentiate these two impulses? Of course, you understand this 10 delta t is higher in impact because it has a 10, and this delta t it has a 1, right? So what this means, this 10 and 1 means. So this represents not the magnitude, but we can call it the strength of the impulse. Strength of the impulse. This represents the strength of the impulse. Now, so is strength similar as magnitude? We'll see. Actually, it's not. It's basically the area under the impulse function that is called strength. So strength is you can say this is actually area under the impulse function. Area under the impulse function, right? Now, so they will not be the magnitude because delta t and 10 delta t, both of them has infinite magnitude. Of course, for 10 delta t, the value of the infinite, that infinite of delta 10 delta t is much higher than delta t. It is actually 10 times higher than delta t, that you can say. But in theoretically, you should say that both of them has an infinite magnitude. But we'll show you that they have different area under each of them. To explain this concept, we will introduce another function which is called rectangular function. So rectangular function, as I have drawn here, you have a rectangular function of width 1. So you have a function which is non-zero, which is a unit in value from minus half to plus half. Uh, so starting from t equal to minus half to t equal to half, the value of f of t is equal to 1, and elsewhere it is 0. So we have written here that f of t is 1. F of t is 1 when you have when t is in between minus half and plus half. Elsewhere it is 0. So this we use a special notation. For example, here we have used delta t to denote or express the impulse function. Similarly, to express the rectangular function, we use rect t. So this rect t function is a rectangular pulse with a duration of 1. So it has duration of 1 second. You see that. So this is the duration. So this rectangular function is located at 0. So t equal to 0. You can say that. So this is 0. T equal to 0. But it has a width. So this one is width, right? So this is actually width of the rectangular pulse. So this rectangular path has a width of 1 second. So, and we express that with rect t, right? Rect t. Now, if you want to express a rectangular path which has a width a, so for example, in we have drawn here, so you have minus a over 2 to plus a over 2, right? So this one has a width of a. So how you express this? How you express that? So in this case, what you should do actually, you replace this t by a. So if you replace t by t over a, right? So that means this t will also be replaced by t over a. So here you have t over a. So which you can simplify that if you take the a in both left and right hand of this inequality symbol, then you should have t from minus a by 2 to plus a by 2, which is precisely this function. So rect t, so I missed one t here, so let me just write that. So here you have t, so rect t over a. So when you have t over a, it has a width of a, right? It has a width of a. So so again, so here we have given an example. So if I ask you to draw rect t over 5, then you should understand that this rectangular path is located at t equal to 0 with the width of 5. So to make the width 5, it should start from minus 2.5 and ends at 2.5 plus 2.5. Elsewhere it is 0. But you can also, if I ask you to draw, for example, 10 rect t over 5, so you will get the same signal. Uh, only difference will be it will have a higher magnitude. So 10 is the magnitude, and this is also from 2.5 to plus 2.5, and it has a width of 5, right? So so what is the area under this rectangle? What is the area under the rectangle? So here you see that we're trying to find the area. So it's very simple, as you know, this rectangular in shape. So if you have a rectangular path with a width of a and height h, then what is the area of this one? So h into a, right? So h, so this is the rectangular path. So symbolically you can write notation wise h rectangular t over a. So it's a rectangular path with a height h or amplitude h, whatever you want to call it. So the area will be area of this rectangular path is h into a, right? Now if you want to make the area 1, right, what will be the value of h? You can easily find it out. So h into a, you want to make it 1 unit area. In that case, h will be equal to 1 over a, right? So what we will try to do now, we want to reduce we want to decrease the value of a without changing the area under this rectangular path. So what happens when we reduce width of the path without changing the area? So the area is always constant. We want to keep it constant, but we want to reduce the value of a. So what it will do? It will make the h. It will make the h higher, right? It will make the h higher. So you want to decrease the value of a. You want to decrease the value of a, right? Without changing the area. So what it will make the h. So since h equal to 1 over a, because a into 1 over a equal to 1, right? A into 1 over a. So a, if you have a into 1 over a, so that is the area 1. So if you now in this case, if you reduce a, obviously 1 over a will increase, so that you have 1. So we have given here a table for your understanding. So if you have a equal to 1, h equal to, in that case, will be 1 to make the area 1. if you reduce the value of a 0.1, that is 1 over 10, then h has to be 10. So 10 into 1 over 10 equal to it will make the area 1. Similarly, if you have a smaller value, a 0.01, the h has to be 100, so it should be much higher, and it will be again 1. If you further reduce it 0.001, then h will be much higher again. So the same amount, right? So if you reduce a by 1000 times, h has to be increased by 1000 times, and to make the area 1. So that is, graphically you have shown here. So in this case, you have initially, so this is minus a by 2a, and the height is 1 by a. This height is always 1 by a, right? So if you reduce it, then it will, in this case, you see we have drawn here. If you reduce a, so initially we reduce it by, the width is reduced by half, and then the height will be increased by 2 times, right? If you reduce by 4 times the width, then height will be increased by also 4 times, right? So, and slowly what will happen, it will look like an impulse. It will look like, I cannot draw it here, so it will look like an impulse at 0. So basically it will be like this. It will be an impulse. It's a very high value, right? And you can use an arrow. So that means this is your delta t, right? So you can, so summary is that, so if you have a rectangular pulse, let me just write down that in mathematical what happens. So you have a rectangular pulse with the width of a, and height or the amplitude is 1 over a. Now if you have a limit a tends to 0, then this rectangular pulse, it will be equal to delta t, because the duration of delta t is that it has it is located at t equal to 0, and it has high magnitude, infinite magnitude in fact, and it has area under this delta t is 1. So this has unit strength. So it has unit strength, GTH. So that means it has the area under this area, so area under delta t is 1, right? So now you understand that delta t has an area. Delta t has an area of 1. So we write this way. So delta t, if you integrate delta t, you should get 1, right? So that is what we write. So that is another property of delta t. So delta t, the area under delta t is 1, so you can write it in terms of integration, because you know that integration, the area under the curve is given by integration. For example, if you have a signal, right, f of t. If you have a signal f of t, then you can write, for example, you want to find out the area under this curve. So from a to b, how do you find it out? As you know that you integrate f of t, right, from a to b, and that gives you the area. This gives you the area under the curve. So in the similar fashion, if you have a delta t, function, so if you have a delta t, for example, you have a delta t, right, and so this is 0. So if you integrate this delta t from minus infinity to plus infinity, then the area of delta t will be 1. So this is another property, uh, but we'll see that you can actually reduce the limit of this integration because your delta is located at 0. So if you just instead of minus infinity plus infinity, because all the area here, this is actually there is the value of this area is 0. So if you can just say that, you can also say that. So we'll actually explain in the line below. So I'm coming to that point. Now, this delta t is located at 0, but if you want to shift it at t naught, then you use this notation. And in that case, your impulse will be located at t naught. So this is t, and impulse is shifted at t naught. So you have a now shifted impulse. So this is your delta t minus t naught. Delta t minus t naught. It's a shifted impulse, right? Okay, so few more properties. Let's go through those properties. So now, if you have a delta function, an impulse function, and if you want to multiply any other signal with delta t, then what you should get? What is the outcome? So let's try to explain this. What you mean by that? So you have a signal. So you have a signal. Maybe this is your signal, right? F of t, and then you have a delta function, right? So this is your uh, delta function, and this is delta t. So if you multiply, you see this delta t is located at 0, at t equal to 0. So if you multiply this delta t function with f of t, what you should get? So the answer is that, so you understand that the value of delta t is 0 everywhere. So, right? So now if you multiply this part all 0 with f of t here, it will be 0. So let me just draw the outcome here. So so you should get actually another impulse, right? At t equal to 0, you should get t equal to 0. So t equal to 0, so the value, so you should get an impulse, because everywhere it is 0. Only thing is that at t equal to 0 it is not equal to 0. So it is an infinite magnitude, and so you multiply that infinite magnitude with the value of, so at t equal to 0, this function has a value, and this function has a value, and this is here f0, right? This is f0 here. So that means this f0 should multiply with delta t. So you should get an impulse, right? So now the strength of the impulse will change. So it will be f0 delta t, right? So again, so if you multiply a signal with an impulse, you should get an impulse, and that impulse will have a strength of the value of the function where the impulse is located. So here the impulse is located at t equal to 0, the value of function will be f0, right? But if you have an impulse which is located at t naught, then you should, after multiplication, you should get f t naught into delta t minus t naught. So let me just write it down. So here you should get f0. So here you should get f0 delta t, right? So this is now the new strength of the impulse. And if you have f of t delta t minus t naught, so what will be the result of this one? So this is actually, so now the impulse is located at t naught, right? So your function value of the function at t naught is f t naught, right? And it will be an impulse delta t minus t naught. So the strength of the impulse is f t naught. Okay. Okay. Now, so now the properties that we have explained uh, earlier, the area under delta t. So we little bit we change it here. So, and it's very easy to understand here. So you have a f of t, a function, and you multiply that with delta t minus t naught. We multiply that by delta t minus t naught, right? So, so after integration, what you should get? So let me just work it out. It is very easy. So your impulse is located at t naught, and here we have given a what we call we assume that. So this is basically assumption, right? We assume that your t naught is located between t1 and t2, right? So let me just draw it out. So if you have f of t, again you have f of t here, and then you have an impulse. So impulse is at maybe at t naught, right? So this is your t naught, and this is t, right? So if you multiply these two signals, then what you will get? So we have already written, right? So the ft uh, and then you have t1. So suppose this is your t1 and this is your t2. It can be any value, right? As long as t naught is in between t1 and t2. So this t naught, as we've written here, this t naught is in between. It's a point in time which is in between t1 and t2. So now if you first you have to multiply, right? If you multiply these two, then the result is basically so this is a change strength. So it is f t naught delta t minus t naught. This is a t naught. Now if you integrate this one, what you should get? So this is an impulse which is a strength f t naught. That means the area under this impulse is just f t naught. So the answer will be here f t naught, right? So the answer here is f t naught. Again, you can actually explain. So let me just explain it more. So we want to find out f of t delta t minus t naught dt. What is value of, so let's plot it again. So you have, so at t naught, so this is a value here, you get f t naught, right? And you have an impulse is at t naught. So this is shifted impulse delta t minus t naught, right? So now if you multiply, you should get another impulse at t naught, but it will have a different strength. So strength depends on f t naught, right? So you should have now f t naught, the strength is f t naught delta t minus t naught, right? So that means you can write from this integration f t naught delta t minus t naught dt from t naught t1 to t2. So you can say that f t naught, this one with respect to t, this is a constant, right? So you can take it out, f t naught integration from t1 to t2 delta t minus t naught dt, right? And that means you are trying to find out within t1 and t2. As I said that we assume that t2 t naught is located between any point in between t1 and t2. So that means within t1 and t2 your impulse is located, and this impulse has a strength of unit, right? So that means you multiply ft naught with 1, which gives you ft naught. So without doing this simplification in that way, you can directly write here also, because you have a strength of delta function which is ft naught, and area under this one you can directly write here. You can, if you want, ft naught. So that is precisely the formula that we want to derive. So these are the properties. There are more properties, advanced properties like a doublet or different first order differentiation of a delta function, but we will not cover here.